Hello everybody, thank you for watching. This is our 9.4 video on the kinetic molecular theory and pressure conversions. In this video, you'll be able to describe the motion of particles using our kinetic molecular theory and then talk about gas pressure. Let's first start talking about the kinetic molecular theory of gases. In general, it's talking about how gases are composed of particles that are always in constant motion. And the actual theory has three basic assumptions. The first assumption is a gas is composed of particles. These particles are considered to be hard spheres, and there are actually a lot of space between each particle. So they're relatively far apart with a lot of empty space between them. The second part of the theory talks about how these particles that are really far apart from each other are in constant, rapid motion. And usually they're traveling in straight lines independent of one another. So one might be moving in one direction, the other one might be moving in a different direction. The main idea is that all of these are in rapid, constant motion. They're just moving or all around a given area. The third part about the theory is that all of the collisions are perfectly elastic. So what I mean by that is when these particles are colliding with one another, there's no loss of energy. So the average kinetic energy remains the same. So for example, pretend this particle is moving at 1 meter per second, and this particle is also moving at 1 meter per second. When they come close to each other and they collide, they're going to hit each other, but this collision is perfectly elastic. So they're going to just keep moving at the same speed of 1 meter per second. No energy is lost, so the average kinetic energy remains the same. So they're going to be traveling at the same speed. You can take a look at all of these particles. Since they're moving independent from one another, they're going to most likely collide with one another, but when they do, the collisions are elastic and no energy is lost. So they're always going to be traveling at the same speed. The last thing we're going to talk about in this video is gas pressure. So pretend we have a gas molecule. So what is gas pressure? Gas pressure is defined by the force exerted by a gas per unit surface area. So when we talk about pressure, pressure is proportional to the number of molecular collisions and the force of the collisions in a given area. So the more collisions you have, the more pressure you have. Not collisions between particles though. The more collisions of a gas molecule within the walls of the container, the higher the pressure. So the more collisions or more molecules that are hitting the walls of the container, you're going to have a higher pressure. So pretend we have one molecule that's bouncing all around one given area. You can see that the amount of collisions for that molecule versus a molecule where you have two, or let's say even three particles, you're going to have an increase of pressure because you have more collisions on the walls of the container. So that's our key idea. The more collisions of a gas particle within the walls of the container, the higher the pressure. So when we relate gas pressure, we can finally talk about our atmospheric pressure. So here we have a diagram where we have these different particles that are colliding at a given surface area. So we talk about Mount Everest, and we also talk about the higher atmosphere. So in general, the definition of atmospheric pressure is the pressure that is all around us at the same time. So the reason we have atmospheric pressure is because of the collisions within the molecules in the air over a given object. All right, so we know that at sea level, which is where we are, which is right here, you can see that there are a lot of particles that are going to be hitting here. So therefore, you're going to have lots of collisions. So you're going to have very high pressure, which you can see we have 101 kilopascals. What about if you're up in the mountains like Mount Everest? You can see that there's very less particles now. So you're going to have less collisions up there. Because you have less collisions, you're going to have a lower pressure. So back to our key idea, the more collisions you have, the higher the pressure. The last thing we want to talk about is some instruments we use to measure atmospheric pressure. We have a barometer, which is used to measure atmospheric pressure in different units. We have lots of pressure units, and we're going to learn how to convert these units from millimeters of mercury back into different types of pressure units. So one thing you need to be able to do is convert our pressure units into different types of units. So we have a 1 ATM, with the abbreviation is ATM. We have pascals, which is PA, 101,325, or we can have 101.3 kilopascals. We can have 760 millimeters of mercury or Thor, it means the same thing. And all of this equals 14.7 psi, right? So what if we wanted to convert, or we know that on the top of Mount Everest, the atmospheric pressure can be as low as 4.89 psi. What is the pressure expressed in atmospheres? So you need to do some dimensional analysis and conversions. So we start with 4.89 psi, and we know that for 1 atmosphere, that equals 14.7 psi. So psi's are going to cancel. We do some multiplication and division, and we get an answer of 0.333 psi. Go ahead and try this you-try problem and come back to see if you get this pressure conversion problem correct. So this is the work for the pressure conversion. We're converting 761.3 millimeters of mercury into pascals. This is the conversion that comes from up here. We have 760 millimeters mercury for every 101,325 pascals. When we do some conversions and cross out some units, we're going to see we're going to have this many pascals. And that concludes our video for today. Thank you for watching.